Okay, so then I can move all my y's to one side and my t's to the other, including the dy and the dt. So this is going to be y to the negative 2 dy equals t plus 3 dt. So I just divided both sides by y squared, multiplied both sides by dt. Then we integrate both sides. And y to the negative 2, when I integrate it, becomes negative 1 over y, negative y to the negative 1. And the antiderivative of t plus 3 would be t squared plus 3t plus c. Now, technically, there's a plus c on both sides, but I just smush them both together into one c on the left. And now I want to solve this equation for y. So I'm going to have y equals negative 1 over t squared plus 3t plus c. Yes, thank you. Yep, antiderivative of t is t squared over 2. Okay, so now I use my initial condition to figure out what c has to be. My initial condition was y of 0 equals negative 1. So y of 0 would be negative 1 over c, which is negative 1, which means that c is 1. And take your c, plug that back in. So we get y equals negative 1 over 1/2 t squared plus 3t plus 1. Yeah. Nice little separation of variables problem. Why? You don't like having like a confidence builder as the first one?
No, because you open up the next 3 pages and it's like...
So 2003 number 2, this was actually on your take-home test that I just gave back, and I'm pretty sure most of you got it. So I don't know if we need to go over it, but so we're supposed to determine all equilibrium points of the system. That's part A. So in that case, you just set both equations to 0, and we have to solve for x and y. All right, so we have a nice linear equation over here. Y equals 3x. Take your 3x, plug it in for y in the other equation. Okay, so we have 10 minus x squared minus 9x squared is minus 10x squared. And we end up with x equals plus or minus 1. Factor out the 10, move the 10 over, move 10 over, divide by 10, square root. All right, so then you take, if x is positive 1, y equals 3. And if x is negative 1, y equals negative 3. So those are our 2 points, 1, 3, and negative 1, negative 3. All right, so part B is identify the types of the equilibrium points you found. So determine if it's a sink or a saddle or a source, etc. Okay. So I'm going to write this down again. X prime is 10 minus. So to determine the type of the equilibrium point in a nonlinear system, you have to linearize at the equilibrium point. So I have to linearize which means throw out any higher order terms. Which we do by making the Jacobian matrix, which is df dx, df dy, dg dx, dg dy. Okay, so when I take the derivative of the x prime equation with respect to x, I get 10 minus, nope, the 10 goes away. I get negative 2x. When I take the same derivative, the derivative of the same function but with respect to y, I get negative 2y. And then the derivative of the y prime equation with respect to x is 3, and with respect to y is negative 1. All right, so then we evaluate the Jacobian at each equilibrium point. So we'll do the Jacobian evaluated at 1, 3 to start, one of the equilibrium points. So we get negative 2, negative 6, 3, negative 1. The characteristic equation would be negative 2 minus lambda times negative 1 minus lambda minus negative 18, so plus 18 equals 0. Solve for lambda, and that will tell us what kind of equilibrium point we have. So this says 2 plus 18, that gives me plus 20. And then I have minus 2 lambda plus lambda is minus lambda. And then lambda squared. Yep, it should be. Thank you. Yeah, so that's 2 lambda plus lambda is 3 lambda equals 0. And that, does that factor? No. Okay, so we use the quadratic formula. We get lambda equals negative 3 plus or minus the square root of 9 minus 4 times 1 times 20 all over 2. So 9 minus 80 is a negative. So you have a negative under the square root, which means we're going to have some kind of spiral, right? Some kind of periodic solution. The real part's negative, so this is a spiral sink. Then we do the exact same analysis, but now I'm going to evaluate the Jacobian at the other equilibrium point, negative 1, negative 3. So I'm going to have 2, 6, 3, negative 1. And my characteristic equation would be 2 minus lambda, negative 1 minus lambda, minus 18. So that's negative 2, so this is going to be negative 20. Minus lambda, minus 2 lambda plus lambda is minus lambda. Lambda squared equals 0. And this factors to lambda minus 5, lambda plus 4. So we get lambda equals negative 4 and 5 are my two eigenvalues, which tells you what about the equilibrium point. It's a saddle. Both are real, one positive, one negative. You have a saddle. Okay, determine the type of equilibrium point at the origin and find all straight line solutions. Okay, so that means I got to find the eigenvalues. First step. So my coefficient matrix is going to be 0, 1, negative 4, negative 4. If I were to write that into matrix notation. And I have to take the determinant, set it equal to 0 to get the characteristic equation. Sorry, not determinant of with the lambdas in there, so I won't write it like that yet. So to get the characteristic equation, I do the determinant of 0 minus lambda, 1, -4, -4 minus lambda, equal to 0. So I have negative lambda times -4 minus lambda minus -4 equals 0. So I have 4 lambda plus lambda squared plus 4 equals 0. That factors to lambda plus 2 squared. So I get lambda equals -2 is a repeated eigenvalue. Just have one eigenvalue, which means there's only one straight line solution. I need the eigenvector to be able to write it down. So in general, to find eigenvectors, you have to solve AV equals lambda V. And you do that for each lambda, which we only have one of in this case. A is my coefficient matrix. 0, 1, -4, -4 times xy equals lambda, which is -2 xy. Okay, so 0x plus y equals -2x, and -4x minus 4y equals -2y. And those two equations are consistent. They have the exact same information. They're equivalent. So an eigenvalue, an eigenvector would be 1, -2. So straight line solutions would be y equals in general, straight line solutions are e to the lambda t v for any eigenvector, right? And any eigenvector will make this a straight line solution, so you can throw a k in front because any multiple of the one particular eigenvector you chose is also an eigenvector. Okay, so in this case, I'm going to have y equals k e to the -2t times my eigenvector of 1, -2. And they wrote the solutions a little bit differently in here because they basically distributed the k into the eigenvector, except they called it x because, yeah, that's just a general eigenvector. Yeah, instead of choosing one particular one and then taking multiples by using a k. They didn't write a k, and in here they put x and -2x. Yeah. It's just another way of writing all the multiples of this eigenvector. Yeah. No, just redundant. Yeah. Okay, and then we're supposed to sketch the phase portrait. So this is going to be x and y. And we know we have a straight line solution that's on the eigenvector 1, -2. So here's a straight line solution. And that corresponds to a negative eigenvalue, so the solutions are going in towards the origin. And then the repeated eigenvalue case is one that is like the boundary between a spiral sink and a real sink. So we have to decide, so they're all going to swirl in, but the question is which direction do they swirl into? So that's a star source, which is when I think No.
I saw that on the internet.
That's a different case. That's not the repeated eigenvalue case. I think that happens when lambda is 0. Yeah. Yeah. So the repeated eigenvalue is the boundary between the spiral sink and the real sink. So these things, like, they're going to try to spiral, but then the straight line solution like gets in the way and sends them directly to the origin. So we just have to decide which way it swirls, because it could either go like that, or with that same initial value, it could swirl in like that, and we have to decide which direction it swirls in. So how could we decide which one of those is the solution? Plug in a point and find out which direction it's moving. So pick any point in, say, the first quadrant. 1, 1 would be an easy one, right, to plug in. So we go back and look at our equation. If I plug in 1, 1 for x, y, x prime is going to be 1, and y prime is going to be -8. Okay, so at 1, 1, my vector is 1, -8. So it's pointing down like that, which means that it's going to have to swirl this way first and then come back in towards the origin. So these are, that was maybe a little bit too much swirl there. Something like that. And then if we start in this quadrant, these are going to swirl the other way, like that. So in general, they're going to be parallel to the eigen vector in one direction and come in tangent in the other direction. So they start out parallel and come in tangent. And then if you start like right here, it would just come in tangent. No, sorry, that's wrong. No, they all do that, yeah. Oh, thanks. Oh, there's a part C, okay. Part C, plot the initial conditions, 0, 4, 4, 1, 2, -4, -5, 0 on your phase portrait. Okay, so 0, 4 would be like right here. Maybe I'll do these in a different color. And then B is 4, 1. And C is 2, -4. And D is -5, 0. Over here. Okay, so we plotted them on the phase portrait. And then we're supposed to plot x of t and y of t graphs for each of these initial conditions. So it would help if I had trajectories to follow. So for each of them, I'm going to draw a trajectory. So this one would be like, starts out parallel to that, and it's going to swirl in like that. And C, yeah, C is just going to come in because it would have like gone, whoo. Yeah, C is already on its way in, really close to the. It's on a trajectory that like came like this.
No, that's going the wrong way. Right? On that side of the line, it's spiral.
Oh. Yeah. C is on the line. I should have, yeah. C is 2, -4, which is on the straight line solution. If I was. Mm-hmm. Yeah, I guess it would have to like It's got to come around like that. Yeah.
No, why wouldn't it go parallel, just stay C, and then just have a little curve at the end? We just put the short.
Oh, yeah, yeah.
Isn't that
Yeah, yeah. So like swirling like that. Yeah. Yeah. Mhm. Yeah.
I mean, if you extended those two to the left, they're just going straight along.
Mhm. Yeah. Okay, so then D would have to go like that. Something like that. And C just goes directly to the origin. Okay, so let's see, for A, so first let's look at what happens to the X coordinate as we follow the trajectory that starts at A. So the X coordinate starts at 1, right? The X coordinate of A? Oh yeah, why did I plot 1 for? Okay. 0, 4 is like here. There we go. Okay, so A starts at 0. Its X coordinate starts at 0, so the first point is right there. Let's do it in a different color. Okay, so then what happens to the X coordinates? They get bigger and bigger and bigger until somewhere over here, yeah. And then they get smaller and smaller and smaller, head back to 0. Bigger and bigger, bigger, smaller and smaller, smaller. Right, time's not represented on the graph. No, time is not in this picture at all. You can't tell. Yeah. We could, yeah. Yeah. Okay, so then if I start at A, I want to look at what happens to its Y coordinates. Okay, so the Y coordinate of A starts at 4, and then what happens to the Y coordinates? They're getting smaller and smaller and smaller. They're approaching 0, right? And then they actually get negative, and then they come back up to 0. So when I plot Y, it's going to start at 4. They get smaller and smaller and smaller. They hit 0. They actually get negative for a bit, and then they come back up and approach 0. Yeah. Yeah. Mhm.
So if there's a line y that
Yeah.
if it doesn't hit that line, they're not.
Okay, so here's the line y equals x.
So B is not going to.
So in B, the solutions never cross. Oh, that makes sense. Yeah. Okay, good. That's very helpful.
It helps you when you're drawing.
To know that. So here, my x. Yeah. Yeah. Here, my x and y crossed each other because in my initial condition A, they cross the line y equals x. Yeah, right. They cross twice. Yeah. Yeah. Good. It does. Won't touch each other. Yeah. Yeah. So let's look at what happens with B. Okay, so with B, my x coordinate starts at 4. Okay, so my x-coordinate starts at 4. I'll put that on my graph. Then what happens to the x-coordinates of b as we follow that trajectory? They get slightly bigger, and then they head back in towards 0. Okay, so we'll draw that. X-coordinates get slightly bigger, head back towards 0. Okay, and then y of t. For b, what happens to the y-coordinate? It starts at -1. Oh, did I plot b wrong? I did. Oh, it's 4, 1. Okay. So b starts at 1, and then its y-coordinate starts at 1. Then what happens to its y-coordinates? They get smaller. They head down. They pass 0. They get negative, and then they head back in towards 0. Okay. So these are going to start at 1. They just decrease. They get negative for a bit, and then they just come back in towards 0. And they didn't cross, as predicted. Good. Do we need to do all of these, or do you get the idea? Okay. All right, let's move on to number 4. General solution to dy dt equals -2y plus 5 cosine 3t. Okay, so this is a non-homogeneous linear differential equation. So if I move the 2y over, we get that. That's sort of the typical way that we write this kind of thing. We can, yes, if you want to use that method, we can. So we have a 3-step process, right? Solve the associated homogeneous equation, find a particular solution to the non-homogeneous, and then step 3 is add them together. Okay, so this is 1, 2, 3. And the general solution to when it equals 0, and find a particular solution by setting it equal to the actual forcing function. And then 3, add 1 and 2. So step 1 is sort of the easiest, so let's start there. We need to solve dy dt plus 2y equals 0. What do you think? Okay, so we can move the 2y over. We have y prime equals -2y e to the minus 2t. Yeah, you can solve by separation of variables. And we've saw at the beginning of the course, we solved lots and lots of equations like this, and it always comes out to y of t is some constant times e to the -2t. If you left that as a dy dt, we would just move the dy over, divide both sides by y. That's what you get. Okay, so you've got the associated homogeneous equation solved. Half of the problem's done. Step 2 is to find a particular solution to dy dt plus 2y equals 5 cosine 3t. So in general, you guess a function, because this is where we have to do lucky guess, right? We have to come up with or a smart guess, I should call it. I have to come up with a function, guess a function that will solve this. And it usually takes on the same form or a closely related form to that forcing function. So yes, we could complexify because it's easy to make guesses for exponentials. So we could write this as dy dt plus 2y equals 5e to the 3it. That says 5e to the 3it is 5 times cosine 3t plus I sine 3t. So those are not equivalent equations. I have replaced the 5 cosine 3t with this guy, but these are not equal. Yes, we could also try to make our guess directly from here. And a linear combination of sines and cosines will work. You could do a cosine 3t plus b sine 3t, and you can do method of undetermined coefficients from there, rather than complexifying. Do you want to do both, or? I mean, this is how we did it in class, because we needed it for something else. So we will continue this way. All right, so now that I've written a different equation, this is a different equation, but its solution is gonna have a real part and an imaginary part, because this is a complex exponential. So the solution to this guy will have a real part and an imaginary part, and I'm gonna be interested in just the real part. The real part of this solution is the solution to this. So let's write that down. Will be the cosine part, yeah, because any complex exponential can be written as cosine theta plus I sine theta, and we want the cosine part. Yeah. So the real part of this solution is solution of original. Okay, so what should I guess? As a solution to this differential equation, what would I guess? A e to the 3it. Yeah. So when it's an exponential, you just guess a multiple of that same exponential. All right, so y prime would be (3ia), yeah. 3ia e to the 3it. So that's y prime, that's the derivative of this guy. And then plus 2y, so that would be 2a e to the 3it. Trying to force this to equal 5e to the 3it. So I can combine these two, factor out the e to the 3it. Yes, but I'm trying to equate the coefficients, right? So I'm going to keep, so this is going to be 3ia plus 2a equals 5e to the 3it. So then set the coefficients equal 3ia plus 2a equals 5. So a equals 5 over 3i plus 2. All right, so if you remember from maybe a college algebra class, the way you simplify when you have a complex number in the denominator is you multiply top and bottom by the complex conjugate. Okay, so a is 5 over 2 plus 3i. I'm going to multiply the top and bottom by 2 minus 3i. So this becomes 10 minus 15i. And when you FOIL the bottom, all the i's go away. That's the whole idea, is that because I squared is -1, we set this up so that the outer and the inner cancel, and then the last gives you an I squared, which is just a real number. Yeah. We like to write all of our complex numbers in the form something plus something I. And 5 over 2 plus 3i doesn't really fit that standard form of a complex number.
So you can't just...
You could leave it like that. your arithmetic's just going to get messy. So we kind of simplify as we go.
And it's harder to pick off the part.
Yeah, yes, right. You have to have it written in the a plus bi form in order to grab the real or the imaginary part. So when you FOIL these, you get 2 plus 9, which is 11, 13. So we have 10 13ths minus 15 13ths I. So we wrote it in the standard form there. Okay, so I don't know, we're partway through here. All right, so now my solution, right, my y complex, my guess was a e to the 3it, and I now have an a. 10 13ths minus 15 13ths I times e to the 3it. So there's my complex solution, the solution to the complexified equation. Now I'm going to decomplexify it, right? Write it in terms of sines and cosines, grab the real part, which is the cosine. Yeah. So I'm going to have 10 13ths minus 15 13ths I. And then I'm going to rewrite e to the 3it using Euler's formula. So it's going to be cosine 3t plus I sine 3t. So yeah, that was part of the forcing function, but my guess was I don't know what coefficient's going to make it equal that. So yeah, that was the a. Okay, so now I FOIL this thing. I have to multiply this all out so that I can grab the real part. So FOIL, I have 10 13ths cosine 3t plus 10 13ths I sine 3t. Yes. Oh, thank you. Okay, so plus 10 13ths I sine 3t minus 15 13ths I cosine 3t plus 15 13ths sine 3t. So I took the I and I made an I squared, and I used that to just change the sign. So I didn't write it down. So now what I want is the real part of this solution, right? So I want the real part, and that's going to be my actual solution. So I only grab the things that don't have i's in them, this piece, and this piece. So I have 10 13ths cosine 3t plus 15 13ths sine 3t. That's my y particular. All right, so then I have to add that to my general solution of the homogeneous, and I'm done. Step 3 is that y general is the result from step 1, which was k e to the negative 2t, plus the results from step 2, 10 13ths cosine 3t plus 15 13ths sine 3t. Yeah, probably. No. Nope. So when you're solving a non-homogeneous linear differential equation, your 3-step process is solve the associated homogeneous, generally, find a particular solution to the non-homogeneous, and then add them. You don't have to put a multiple on the particular solution. Yes. All right, so B, give a one-sentence justification of the fact that all solutions tend toward a steady-state solution as t goes to infinity. So as t goes to infinity, this is the natural response of the equation, right? The non-homogeneous or, sorry, the homogeneous or unforced equation. This is its solution, which as t goes to infinity goes to 0. So the natural response dies out, just leaving the sinusoidal response, which is the forced response. Oh yeah, calculate the amplitude of the steady state solution. So yeah, we didn't really, the day that we did this, we did do one where we took that combination of sines and cosines and we did a ton of like trig manipulation to try to make it an equation that had, so we could read off the beats and the, yeah, so I'm not going to put that on the test, but you can do it.
So you want it all written in terms of one trig?
Well, there are shortcuts that we never really discussed. Yeah, but the steady, yeah, that was the idea behind it. And if you go back to the complex solution, AE to the 3IT, right? So this is a trig function, but written in complexified form. This is the amplitude, right? That's the coefficient on your sines and cosines. So we want to find the distance of this thing. So we could call, this is A, right? The amplitude is the magnitude of A. So 10/13 minus 5/13 I in the real and imaginary plane would be like here. And then you want to find that length. That's going to be your amplitude. So use the Pythagorean theorem. 10/13 squared plus 5/13 squared equals your amplitude squared. 15/13, yeah. And you get that this is approximately 1.39. But don't worry about too much about it. I won't put something like that on the test. I promise. Okay, number 5. Consider the initial value problem. Y double prime plus 4y prime. Describe the long-term behavior of the solution. You need not do a lot of computation to answer this part. Okay, so the long-term behavior is going to approach that function. Okay, because this is a harmonic oscillator, mass 1, damping coefficient 4, and spring constant 9. So this is the harmonic oscillator with positive damping coefficient, which means it's going to die out. Right. So when I set the unforced equation to 0, when I set the equation to 0, I'm going to get some function that dies out over time, leaving only this as my forced response that's going to dictate the behavior of the mass on the spring over time. Yeah. 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 We actually didn't study that, so you don't have to worry about it. Okay, so that's part A. This is long-term. Well, the solution to this thing will be the long-term. We'll say dictates long-term behavior, which means it will be sinusoidal, because when the forcing function is sinusoidal, the solution would be sinusoidal. Okay, so we want the inverse Laplace of s plus 6 over s squared plus 4s plus 9. Okay, so the whole idea with inverse Laplace is that you have to make it look like something from the table, or something that we happen to know the inverse Laplace of, which is not very many things. All we have is 3 or 4 entries in the table right now. So look at the table. Is there anything that it could possibly look like? Anything that has, if s squared plus 4s plus 9 factored, I would use partial fractions to get my two denominators to be linear. But does s squared plus 4s plus 9 factor? So we complete the square. So when the only way you can take an inverse Laplace transform of something that has a quadratic in the denominator is if it looks like a particular way. Okay, so let's write down the inverse Laplace of, who's got a table? Yeah, I think it was last class. Yeah, thank you. Of omega over s minus a squared plus omega squared. If I can make it look like that, it is e to the at sine omega t. Or there's another candidate, close, it's s minus a over s minus a squared plus omega squared. And in that case, it's e to the at sine omega t. Oh yeah, that one was sine. Cosine omega t. Okay. So these are the only two candidates. So I'm looking through the table and I'm trying to figure out which of the entries in the table can I make this look like. Okay, so these are the only things, because they're the only things that have something in the denominator squared, right? So I'm going to try to make this look like one of these. So you start by completing the square in the denominator. So we get the inverse Laplace of s plus 6 over, and when I complete the square here, I'm going to get s plus 2 squared. So that would give me s squared plus 4s plus 4. So then I have to also subtract the 4, so I have plus 5. All right, so that's close. I have s minus a squared plus omega squared. So I've got my denominator kind of looking like one of these, where a would be -2 and omega would be square root 5. But I need my numerator to either be s minus a, so an s plus 2, or an omega square root 5. It's easier to make an s plus 2, so let's do that. S minus negative 2, yeah. So I'm going to rewrite my numerator as s plus 2 plus 4. Because I wanted this to match this, right? In order to make it look like what's in the table. The A here and the A here have to be the same. Okay, so instead of s plus 6, I wrote s plus 2 plus 4. Okay, so now when you have a single denominator, you can divide that denominator into both pieces of your numerator. So I could write this as the inverse Laplace of s plus 2 over s plus 2 squared plus 5 plus 4 over s plus 2 squared plus 5. So that's just rules of fractions. When you have, now I have two fractions with the same denominator, you can just add the numerators and you would get that. Okay, so this first term in my inverse Laplace, now I can do that one. That one looks perfect, just like something in the table. This would be e to the negative 2t cosine root 5t. So a is negative 2 and omega is square root 5. Okay, so that we did. So this is e to the negative 2t cosine square root 5t. Plus, so that's the inverse Laplace transform of that, the inverse Laplace transform of this, which does not look perfectly like something in the table yet. So I just have a constant on top, so I can't make it look like s plus 2 on top. There's nothing I can do. But if that constant were a square root 5 instead of a 4, it would look just like the sign in this one. It would look just like this one. Because if that's a 5, omega squared is 5. If my numerator were a square root 5, it would look just like this. So I'm going to try to do something to it to make that numerator a square root 5 instead of a 4. So let's just make it a square root 5. That's a 5, not an s. Okay. Okay. Yeah, we'll just change it. So square root 5, I made it that, so now I can take the inverse Laplace transform of that, but I have to make some adjustment because you can't just randomly change it, right? Because then it would be different. So if I pull the 4 out here, took that 4, pull it out, and then divide by a square root 5, then the square root 5s cancel, and it's exactly the same as it was before. Right, because constants can come in and out of the Laplace, yeah. So now I've got 4 over square root 5, and then this looks perfectly like something in the table. So it is, which one is it? Sine e to the negative 2t sine square root 5t. And then bring this part down here, e to the negative 2t cosine square root 5t. Yeah, it's not so bad. Yeah, I don't know if we're going to finish this. E to the negative 2s. Yeah.
I'm gonna be here a while.
Okay. Not till 1. Yeah. I hadn't thought about it. I don't care. Would you rather bring your own, or do I can make? I'll have a few. I'll have some.
Like, I mean, there's probably only like 4 or 5 actual
Of the entries in the table, yeah.
So,
Yeah, we only know a few of them that we've worked with. Yeah, so, I mean, you can have a table in addition to your 4 pages of notes. Yeah. Oh, did I say 3 before? Whatever, bring some notes, I don't care. We'll do this one tomorrow. I'm not going to finish it in 5 minutes.